All right, everyone, let's take a look at the homework that we had last night. It was page 538, number 1 to 10. Any issues with those questions on page 538, please? Courtney? 7B, yep. Yep. 10. 9. 7B, 9, 10. Is that it? Yep. 2, 7B, 9, and 10. Is that good? All right, number 2 says, describe how the inverse square law first proposed by Newton for gravitation forces was applied to electrostatic forces by Coulomb. We look at charges and we look at masses. And charges and masses are very analogous to each other. We're going to learn in this unit a lot of things that are really, really similar about charges and masses, and a lot of things that are similar about electrostatics as compared to gravitation. They're really similar things to each other. There's a force that acts between two masses. There's a force that acts between two charges. Coulomb would have taken this equation, this gravitation equation, gm1m2 over r squared, and said, look, if the force between two masses is going to be gm1 m2 over r squared, an inverse square relationship dependent upon the masses, then the force between the charges is going to be an inverse square relationship, but it's not going to be dependent upon the masses, rather it's going to depend upon the charges. So we took the equation, the inverse square equation that Newton had for it, gm1 m2 over r squared, and simply modified it to reflect charges as opposed to masses. He also threw in that different constant, right? K q1 q2 over r squared as opposed to gm1 m2 over r squared. So because charges and masses are really analogous to each other between gravitation and electrostatics, we can take that equation, or Coulomb could take that equation that Newton derived, gm1 m2 over r squared, and apply that to electrostatics, except that he would have had to replace the masses with the charges. Is that okay? Question 7 says, two identical conducting spheres have charges of 5 times 10 to the negative 5 coulombs and 6 times 10 to the negative 5 coulombs and are in fixed positions. I wouldn't say they're identical conducting spheres if they have different charges, but I think we understand the question here, even though it's not worded all that well. And they're 2.00 meters apart. In question A, we weren't asked to do that, but we'll spend a minute just talking about question A as well. Calculate the electrostatic force acting on the two charges. To do question A, it's going to just be K q1 q2 over r squared. The value of q1 is going to be 5 times 10 to the minus 5. And q2 is going to be 6 times 10 to the minus 5. And of course, we've got r, which we have to square, as 2 meters. We calculate that force, and I'm not sure what it works out to be, but it is what it is, right? It's a pretty straightforward question. In question B, we have to find the electrostatic force again. We're going to use the same equation, K q1 q2 over r squared. How does the answer become something different if I'm using the same equation in the same question to find a force? How do we get a different value for B than we do for A? Yep. Why are they different? We're saying that the charges in A are 5 and 6 times 10 to the minus 5. Why are they different in question B than they are in A?
Because they touch together. So
Good. Okay, that's a pretty key word right there. They touch together. When they touch together, what happens? If they're similar size, similar shape, which we can assume they are because they tell me they're identical spheres, right? What's going to happen to them? They're going to balance out, right? And if they balance out, they're going to balance out to be 5.5 times 10 to the minus 5. Right? 5 plus 6 divided by 2, average them out, works out to be 5.5 times 10 to the minus 5. So we're going to do the same thing in question B as we did in question A, except my charges, instead of being 5 and 6, are going to be 5.5 and 5.5. The distance is going to be the same, 2. Don't forget to square that. And then we're going to get a value for force, which is different than the value that we got in question A. That one make sense? I can't remember who asked me for that one, but hopefully it makes sense to you. The next question that we have to look at here is question number 9. It's a good question. Somebody was asking me about this one this morning. Somebody, I believe it was in, I think it was in one of my other classes, popped in and asked me about that. It says, a helium nucleus has a positive charge with a magnitude twice that of the charge on the electron. So here's the helium nucleus. The helium nucleus actually has 2 protons. So we're going to say the charge is twice the elementary charge. And then we've got electrons orbiting around it. There would actually be 2 electrons orbiting around it, right? But in different positions. Okay, you don't need to know really that there's 2 electrons orbiting around it. You need to know in the end that there's an electron and then there's a nucleus with twice the charge of an electron. We want to know if the force of how the force of attraction on the nucleus, right, pulled towards the outside, pulled towards the electron, compares to the force of attraction on the electron that's pulled inward. Right? We know that the electron is pulled toward the nucleus. We know that the nucleus is pulled toward the electron. How does the force of attraction between those 2 charges acting on the electron compare with the force of attraction acting on that proton? Or acting on the nucleus, I should say. They're the same. F is equal to kq1 q2 over r squared. That force doesn't distinguish between the 2 objects, between the 2 charges. It says the force on both of them is exactly the same value. Now, can anybody explain to me why it is that the nucleus is affected more by that force? Sorry, why it is that the electron is affected more by that force than the nucleus is? They're both affected, right? But the electron is affected much more than the nucleus is. Can anybody give me a hypothesis as to why that might be, Jordan? Yes, the nucleus is heavier. It's much heavier. It's something in the range of 1,000 times heavier, 10 to the 3 times heavier. So it's going to be affected something like 1,000 times less than the electron is because of its mass, not because of its charge. We don't say the nucleus is affected less because it's twice the charge. We say it's affected less because it's way more massive. All right, good. And finally, question number 10 says, electrical forces are so strong that the combined electrostatic forces of attraction acting on all the negative electrons and positive protons in your body could crush you to the thickness thinner than a piece of paper. Why don't you compress? This is a hard question, but yet an easy question kind of at the same time. It's kind of almost an oxymoron in this question, is that you know, we can have a little bit of trouble with this question, but yet at the same time, when we get that insight that we need to get, it's all of a sudden a ridiculously easy question. Anybody think they have the answer to it? Colin? Yes, kind of, but where does that come from? Where does that balance come from, Ryder? Not just the electrons repel each other, but yeah, the protons repel each other as well. So the electrons repel each other, and the nuclei, which are positively charged because they consist of protons, repel each other. So you've got a whole bunch of forces of attraction, but you've got a whole bunch of forces of repulsion. And Colin, what does that end up giving us, essentially? Right. Essentially no net force. So we end up as we are. I'm sorry? Yeah. We're made up of bazillions of atoms, and there's lots of forces of attraction within those bazillions of atoms, but also lots of forces of repulsion between protons and protons and electrons and electrons. Not to any great extent. I mean, it's always possible. It's always possible to have some unbalanced force, but there's so many of them that a little bit of unbalanced force, you're not even going to notice, right? Statistically, it has to work out statistically that the forces pretty much balance out. Okay, at least balance out enough to the point where you would never notice any kind of difference. Good? No more questions on that? All right, here's your first little bit of homework for tonight, please. There's a little reading. It's about a half a page long on page 537. It has to do with the electrostatic discharge, or arcing, basically. I'd like you to read that, and I believe there's 3 or 4 questions at the end of that. I'd like you to read that and then answer the 3 or 4 questions that appear at the end of it. I've given this before, and for the most part, people don't have any trouble with it, so don't panic about it. You know, if you're not one of those people that like reading, don't sweat it. It's not going to be hard for you. Just read through a third of a page of information, answer a couple questions, and then if you still have a little bit of issue with it, then ask me tomorrow and we'll go over it. Today we're going to shift gears a little bit from electric forces to electric fields. The first time that we've dealt with a field was last year in Physics 20. Does anybody remember what kind of field we dealt with in Physics 20? Gravitational field, right. We're continuing to draw those similarities between electricity and gravity that we did in Physics 20. We talked about gravitational fields last year. Gravitational fields were lines of influence that surrounded an object with mass. The influence surrounding something that has mass. Well, a field in general is the influence around something. An electric field would be the influence around an electric charge. If a gravitational field is the influence surrounding a mass, then the electric field would be the influence surrounding a charge. Both gravitational fields and electric fields have a direction associated with them. In other words, they influence whatever it is that they influence. They influence it in a particular direction. Gravity affects masses downward. If I drop this pen right now, it will move in the direction of the gravitational field. It will move downward. There is a direction associated with the influence of gravity. But there's a direction associated with the influence of electric fields as well. If I put a charged object in the electric field, it will be influenced in a particular direction, either towards whatever's causing the field or away from whatever's causing the field. Because of that, we say that both electric fields and gravity fields are vector fields because they have a direction associated with them. That's as opposed to some other type of fields which influence things but not in a particular direction. Let's say light. Light influences things. Light influences us. But it doesn't influence us in a particular direction. Heat influences us, but it doesn't influence us in a particular direction. Now, don't get mixed up here. Light travels in a particular direction. If I have the light switch off and then I turn it on, light travels from the light bulb towards me, and it travels from the light bulb towards you. It travels in a particular direction, but yet it's a scalar field because it doesn't influence us in a particular direction. Its velocity would be a vector because it moves in a certain direction, but the influence of the light doesn't have a direction associated with it, so we'd say it's a scalar field. Light fields, heat fields, anything that influences us, but not in a particular direction. Fields exist as long as we have something to cause that field. Now, if we're talking about a gravitational field, the object that causes that field would be an object with mass. If we're talking about an electric field, then the object that causes that field would be a what? What's going to cause an electric field? What's going to cause an influence on other charges? A charge, right? Now, when we're talking about a gravitational field, we all have only one kind of producer because there's only one kind of mass. It's positive mass. But we have two kinds of charge. We have positive charge and we have negative charge. So we can have two kinds of producers with the electric fields as compared to the one kind of producer with the gravitational field. Fields exist as long as we have that thing to cause the field. Forces, on the other hand, only exist if there's something to experience that field. Let's use gravity as our analogy for just a second here. The gravitational field of 9.81 meters per second squared exists, or at least roughly 9.81 meters per second squared, exists everywhere around the Earth. That's there no matter what. As long as the Earth is here, that gravitational field is going to be there. Now, there is no gravitational force unless there's something there to feel that field. Right now, where my pen is, where my board marker is, there is a field, and there's also a force of gravity acting on it because there's an object experiencing the field. But if I take that pen away, the field is still there. 9.81 is still there, but there's now no force acting because there's nothing to be forced. A force is a push or a pull. In order to have a force, you need something to be pushed or pulled. If there's nothing to feel that push or pull, there is no force. So in order to have a field, you just got to have a producer. Maybe you got an experiencer too, but you don't need one. In order to have a force, you need a producer, of course, but you also need an experiencer, something to feel that field, something to experience that field. Whether you're talking about gravity or whether you're talking about electrostatics. If we were talking about a gravitational field, the direction would be always toward the producer. We define a gravitational field as the way that an object with mass will move when placed in the field. So if we place an object in the gravitational field and we let it go, it's always going to fall towards the producer. Right? Objects, when you drop them, don't fall up. They fall down, always. So the direction of the gravitational field will always be toward the producer, always the way in which that object with mass will move when placed in the field. Now, the electric field direction can be toward the producer or away from the producer. It depends upon which kind of producer we have. So how is it exactly that we define the direction this time with the electric fields? Well, there's two ways. One is the way that a positive particle would move if placed in the field. I got my two producers up at the top of the page there. If I put a positive producer right here, which way is it going to move as a result of that producer? Put my experiencer, my positive experiencer, nearby this positive producer, which way is the experiencer going to move? This is an easy question. Which way is the green guy going to move? Forget about fields for a second. Just look at what you know. Look at what we did the very first day of this unit. Where's the positive experiencer going to move as a result of this positive producer? It's going to move away from it. So if we define the direction of the field as the way that a positive particle would move when placed in the field, then the field must be away from a positive producer. Because anywhere in that field that I put a positive experiencer, it's going to move away from the producer. Now, if I put a positive experiencer in this field, where's it going to go? Towards it. So the field must be toward the negative producer. That's a bad one. It's got to be toward the negative producer. Does that make sense? What would happen, by the way, if I stuck a little negative experiencer in here? Which way would it go? Towards it, right? Opposite to the direction of the field. What if I put a negative in here? Away from it, opposite to the direction of the field. So the field is the way that a positive particle would move when placed in the field. We'll say negatives move opposite. Negatives always move in the opposite direction to the field. If it's the way that a positive particle would move if placed in the field, then the field always also has to be from positive, away from positive, and toward negative. The way that a mass would move when placed in a gravitational field is the direction of a gravity field or toward the producer. The electric field is the way that a positive would move if placed in the field or away from the positive toward the negative. You see a positive producer up on the board right now. All these little arrows represent the electric field that surrounds that positive producer. Notice that each and every one of those electric field lines are pointing away from the positive producer. Right? They should. We know they should. They always point away from a positive producer, because if I was to put a little positive experiencer in there somewhere, if I was to put one in there, I don't need one in there. We define the direction as the way that a positive would move if it was placed in there. So if I was to put one in there, it would always move away from that producer. Therefore, the field is drawn correctly away from the producer. How would it look, though? How would this field look if I all of a sudden introduced another charge? All of a sudden, now I've got two charges, both positive. Let's move them a little bit so it's all horizontal here. You can see in this case that the electric fields, you don't have to draw this, by the way, because we'll redraw these in just a minute here by hand, okay? Just want you to see what's going on here right now. You can see that the electric fields are going away from both of the positives. But what happens in this little area right here? These field lines are kind of pushing away from each other, right? They can't join up with each other because they're going in opposite directions. So you can see that field lines are going away from the positives on both sides. And it looks the same as just an individual point charge, you know, on the right-hand side of this guy and the left-hand side of this guy. But when we get in the middle here, these field lines are pushing away from each other. So the pattern is going to look something like this. Can you tell me what the net electric field would be in this little area right here? How strong would the electric field be? 0. The electric field is 0 because there are no field lines there. They're all repelling each other. There are no field lines there. If we take a step back from that for a second, that should make sense to us. What's the influence of these charges halfway between them? 0. If we were to put another charge right there where that blue circle is, nothing would happen to it. It's being forced toward or away from the first charge. It's being forced away from the second charge. The net force is 0. The net force is 0 because the net field is 0 halfway in between them. They effectively cancel out. All right. What if we have a positive and a negative? Let's move these again so it's all horizontal here. What if we have a positive and a negative? You can see that the field lines are going away from the positive on the left-hand side. What's happening on the right-hand side? Field lines are all going toward it, right? Away from positive toward the negative. If I was to put a little positive particle here, it would go away from it. A little positive particle here, it would go towards it. So that's right. Well, what's happening in the middle here? The field line that leaves the positive, the field line that goes toward the negative, are now joining up with each other. They're joining up with each other because this time they're pointing in the same direction. So you're going to get a pattern that looks something like this. Finally, what's it going to look like if you have two conducting planes? Two charged plates. Well, you get all kinds of field lines going in every which direction. These plates aren't labeled as positive and negative, okay, but they are charged. I want you to tell me which plate is positive, which plate is negative. Which plate is positive, which plate is negative? Oh, sorry. Yellow is positive. How do you know that? Good. The field is going away from the positive plate, and the field is going toward the negative plate. Now you can see some crazy things happening here. At the edges, we've got some curved lines. Okay, we're not going to focus too much on this stuff. Okay, these curved lines at the edges. Okay, we're not going to focus on these straight lines out here. Okay, they don't concern me too much. Although you can see that those field lines are always pointing away from the positive and toward the negative. The part of this that I'm really concerned with here, that I really want you to focus on here, is in between these plates. Notice these field lines are all pointing from the positive plate to the negative plate. Notice these field lines are also all parallel. That tells us that in this case, we have what we call a uniform field, a field that's the same here, 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 everywhere. The field is the same everywhere. It's a uniform field. Versus all of these other situations that we've looked at here, where the field lines are not parallel to each other, that would be a non-uniform field. The field is stronger in some places, weaker in others. Basically, it goes like this. If the field lines are closer together, the field is stronger. If the field lines are further apart, the field is weaker. If they're parallel, then they stay equidistant apart. So it's a uniform field. If they're not parallel, then they're closer together in some places than they are in others, hence a non-uniform field. Make sense? Let's draw a couple of these diagrams, okay? Question? No, it would. Yeah, the electric field surrounding an electron would be towards it. It would be a weaker field than the electric field surrounding, say, a nucleus. Because a nucleus, well, all but one nuclei. A hydrogen nucleus has only one proton. So the electric field surrounding a hydrogen nucleus would be the same field strength as the electric field surrounding an electron. But if you get any other nucleus that has more protons than just one, then the field strength surrounding a nucleus would be stronger than that surrounding an electron. All right, let's draw a couple pictures here. First, let's go with our positive producer. Our positive producer has a radial field surrounding it, radiates around it, a radial field. And that radial field will point away from the positive producer. Always remember why. If I was to stick a little positive experiencer in there somewhere, which way would it move? Away from that positive. So the field must be away from the positive producer. If I was to put a negative producer in here, and then I was to introduce a little negative experiencer, that little negative experiencer would move away from, a positive experiencer, then it would move towards the negative producer. And we're always hypothetically sticking this little positive experiencer in there. It's going to move away from the positive, it's going to move toward the negative. What happens when I have the positive and the negative close together so that they interact with each other? Well, the positive producer, half of it at least, is going to look the same as it did in the diagram above. The negative experiencer, same thing, toward the experiencer. What happens in the middle? Well, the field line that goes out away from this producer joins up with the field line that goes toward that experiencer. This field line joins up with this field line. This field line that goes away from this producer joins up with this field line. And so on and so on and so on. What if we have two positives that are interacting with each other? Once again, on the outside of it, it's going to look exactly the same as it does just for a positive producer, a single one. But in the middle now, in between these, they're going to interact with each other. These field lines are going to push each other away. They're going to repel each other. So it's going to look something like this. In this diagram right in the middle, the net electric field strength is something. In this diagram, the net electric field strength right in the middle there is 0, because there are no field lines right in the middle. It doesn't experience any kind of field or any kind of force. Finally, one more diagram here. This last diagram is going to involve two charged parallel plates. We'll make the top plate negative and the bottom plate positive, although it doesn't matter. The electric field in between those two plates is going to be a uniform field as opposed to a non-uniform field, as we discussed a minute ago. The field lines are going to point which way? Down or up? Yeah, good. They're pointing upwards, away from the positive and toward the negative. Again, you can see that these are parallel field lines, so the field is uniform. That means anywhere in between those plates, the field is going to be the same strength. Remember, at the edges, we had those curved lines, those non-uniform fields at the edges. But we're mostly concerned with what happens in between the plates, not kind of at the edges. All right, let's take a look at a couple equations here, 3 of them. 3 of them from gravity. Again, we're drawing the connection between gravity and electricity. There are 3 forces that you should recognize from last year in Physics 20. The first one is the force of gravity equation between 2 masses. F is equal to gm1 m2 over r squared. There is an analogous electricity equation, the electric force between 2 charges. And we've talked about that quite a bit this unit so far. It's kq1 q2 over r squared. You can see the structure of these 2 equations is exactly the same. They're both inverse square equations. Inverse square relationships. The only difference really here, besides the constant, is that we're swapping the charges in where the masses were. This second equation, G is equal to big G m over r squared. Does anybody remember from Physics 20 what that is? If not, that's okay. Because I'll tell you what it means if you don't remember, but if you do, then that's even better. Cool? Yeah, it's the producer equation. We want to find the field strength caused by an object with mass, the gravitational field strength surrounding an object with mass, and we have information about whatever that producer is. Then we're going to use that producer equation, G is equal to big G m over r squared. Well, there's an electric field equation that's analogous to that as well. If we want to find the electric field strength surrounding a charge, in other words, surrounding a producer, then we're going to say E. That's the electric field symbol, capital E with an arrow over it. It's a vector field, so don't forget that arrow. Is equal to, anybody want to take a stab at what it might be? Without having ever seen it before in your lives? Jordan? Good. KQ over R squared. The constant's got to get swapped out because we're not dealing with gravity anymore, dealing with electricity, and the m's got to get swapped out for Q as well, but the R squared is going to stay the same. So if you want to find the force between 2 charges, use this one. If you want to find the field strength surrounding an object with charge, surrounding a producer, and you have information about that producer, then use this one. The bottom one's the experiencer equation. That's the equation that you use if you have information about whatever experiences the gravitational field. Go back to the pen and the earth for a second. Okay, when I had that pen held up the pen in front of my face, I said the pen experiences a field and a force. The earth is what causes the gravitational field. If I have information about the earth, then I'll use the producer equation. If I have information about the pen, the experiencer, then I'll use the experiencer equation. Well, the experiencer equation for electricity is going to look like this. E is equal to F over Q. Now let's take a look at a couple of these variables. K obviously is the constant. What does Q stand for here? Yep. Good. It's the charge of the producer. It's not just any charge. Okay, there's 2 charges here, producer and experiencer. That's the charge of the producer. And of course, R is the distance away from the center of the producer that you're trying to find the field strength. Q down here stands for what? It's obviously a charge as well, right? Charge of whatever feels the field, charge of the experiencer. And F would be the electric force experienced. The value of the electric force that's experienced by whatever the experiencer is. If you can do these things in Physics 20 with gravity, then you can do these things in Physics 30 with electricity. It's the same thing, except that we're dealing with charges instead of masses. All right, let's try a problem here on page 548. This one says a sphere with a negative charge of 2.10 times 10 to the minus 6 experiences, we see that word experiences. Okay? That might lead us to the fact that we have an experiencer here, although we'll finish up the question before we decide that for sure. It experiences a force of repulsion of 5.6 times 10 to the negative 2 newtons when it's placed in the electric field produced. Oh, we also have that word produced. Determine the magnitude of the electric field the source charge produces at the sphere. Okay, so that word up here, experiences, doesn't seem to really help us a whole lot because we have produce and experience in the same question. Right? We have two equations that will allow us to find electric field, which is what we're looking for. That third equation, remember, was for electric force. Right, KQ1 Q2 over R squared. That's not what we're going to use here because we're not looking for force. We're looking for field. It's going to be one of the bottom two equations. What do we have more information about, though? The producer or the experiencer? What causes the field or what experiences the field? The experiencer. Okay, we've got the charge of an experiencer. Right, we're going to say that this is QE. It's negative 2.10 times 10 to the negative 6 coulombs. We have a force experienced. So we're going to say that's FE, the force experienced. We want to find the electric field. Now, the electric field produced by this producer is going to be the same as the electric field experienced by this experiencer. So use whichever equation you want as long as you have enough data to fit in it. You're going to get the same answer. Okay? If you end up having enough data to do either equation, then use either one. It doesn't matter. You should get the same answer. Let's use the experiencer equation because we do have more information about the experiencer here. E is equal to F over Q. Now, this is the way that it appears on our data sheet. If it was up to me, I would change it to this. I would put absolute value signs around it because I don't want you to find the direction of this field by this equation. I want you to find the direction of the field, if we have to do that, some other way. The magnitude of the force here is 5.60 times 10 to the minus 2 newtons. I don't care what the direction of it is. The charge, the magnitude is 2.10 times 10 to the minus 6 coulombs. I don't care what the sign of the charge is. Just plug in the absolute values for force and the absolute value for the charge as well. When we do the math on that one, we end up getting 2.67 times 10 to the 4. 2.67 times 10 to the 4. What units would we use here? We haven't talked about the units for electric field yet. Newtons per coulomb, right? Newtons over coulomb. Is that a hard question? Not really, I don't think. If we have information about the producer, use the other equation. If you have information about the experiencer, use this one. Just keep it straight. If you can keep straight the producer and the experiencer, you should be good. I'm going to ask you to do these two questions that appear in our textbook. Page 548, questions 1 and 2. See what you can do with them. We'll take a look at them if we need to. Your homework tonight is page 548, number 1 and 2. The practice problems. Your homework tonight is also that reading on page 537. And since you got a few minutes left to work on this, we might as well assign the remainder of worksheet number 7. Good news is it's only 2 questions, right? Questions 3 and 4 on worksheet number 7. That's it for today, guys.